Well, welcome to this video tutorial on amplifiers. I'm John Fattaruso in the EE department, and the purpose of this video is to go over the basics of electronic amplifiers. I'll throw in a little historical perspective for the fun of it, and we'll go on to discuss the design of an amplifier block that you'll need in your robot design for this lab. So this is the basics of what we think of when we talk about a circuit block that we call an amplifier. Suppose we have some sort of analog signal that represents something in the real world, perhaps an audio signal or a video signal, or some sort of levels from a sensor in your robot. Usually we think of a signal being represented as an electrical voltage or potential level on a node in an electrical network, but sometimes you'll see circuits where the signal is more represented as an electric current rather than a voltage. But in this example case, we have a fairly low-level signal that's represented as a voltage. In this case, this signal only varies about 1 millivolt peak to peak, and if you've seen Professor Kinaird's nice tutorial on reading data sheets, he introduced this triangular symbol, which is commonly used to represent an analog amplifier circuit block. And so in this example case, this amplifier has enough voltage gain through it to boost the level of this input signal up to where now the output level is varying about a volt peak to peak in this example case. So this is an example of an amplifier with a voltage gain factor of about 1,000. And this is ideally what we would like. We'd like a circuit block that basically does a linear multiplication of the input signal times some constant gain factor to give an amplified output signal. So applications for amplifiers. Right now, as I'm dictating this video, I'm wearing one of these headset microphones, and the signal level that comes out of the jack here, for typically in these microphones, is maybe a millivolt or something on that order. Whereas in the computer sound card, when you plug this microphone input into the microphone input jack here, this sound card has an analog to digital converter arranged so that the computer can read the audio stream, but that converter is expecting amplitudes of about a volt. So on this sound card has to be an amplifier device to increase the level of the microphone signal up to where the A to D converter is requiring. Another application for amplification, and probably historically one of the earliest, is in radio reception. Suppose you have a radio signal, electromagnetic wave impinging on this receiving antenna here. If that's a faraway signal, maybe on another continent or something, you may only get microvolts of signal, electrical signal in this amplifier. And if you wanted to play that radio broadcast or radio signal on, say, a speaker system and listen to it, the speakers need about a volt, signals on the order of volts to be audible. So that requires a radio receiver with gains, amplifications into the millions. Of course, there's other signal processing that goes on in radio receivers, filtering and tuning and demodulation and so on. But overlying it all is a tremendous amount of voltage gain in a typical radio receiver. So now on to the amplifier that we'll be needing in our robot design for this lab. You'll be making use of a pH sensor on your water sampling head, and the readings from that pH sensor will need to be routed into one of the analog input pins of the microcontroller board, so that you can read out the pH readings back to your controlling computer. Well, the analog input levels that are expected by the analog to digital converter on these microcontrollers are on the order of volts. And so you're going to need to design an amplifier block that will increase the voltage level generated by these pH sensors to something appropriate for the Arduino board. Well, amplification requires some sort of what we call an active device in electronic networks, and I like little historical perspectives on things. So let's go back in history a bit to look at the very, very first active devices in electronics, and these were, of course, the vacuum tubes invented very early in the 20th century. Here's a picture of a Type 01A vacuum tube, one of the very first commercial units available. This is a picture of a tube actually from my personal historical collection, and it dates back to something around 1910, a little difficult to date it exactly, but the first decade of the 20th century. And then through the ensuing decades, technical development of the vacuum tube continued. You had these big bulb tubes in the 30s and 40s, 1930s and 40s, and in the 50s and 60s, technology developed to what they called miniature tubes back then. We look back and think of these as very bulky devices, but at the time they're called miniature tubes. And then in 1947, the invention of the transistor in Bell Labs came about, and the whole field of solid-state physics, so named because you didn't need a vacuum anymore to produce an active device. So whereas vacuum tubes cost several dollars, transistors can be purchased for fractions of a dollar, especially in these inexpensive plastic packages here, and with tremendous reduction in power requirements and increase in reliability. Well, it takes more than just an active device to make a practical amplifier circuit block. The active device needs some passive devices, resistors and capacitors and so on, around it in order to bias them up and produce a practical working amplifier circuit. We won't be dealing with any of these sorts of circuits in this lab, but this is just a heads up for those that are going on to study further double E courses. You'll be analyzing and designing circuits like this. The voltage gain that you might expect from each one of these stages here is maybe 20 or 50 or 100 or so, and if higher voltage gains are needed, stages can be cascaded like this. So in this lab class, the amplifier that we're going to be using is in an integrated circuit form, a very high gain amplifier called an operational amplifier. And this is an example IC op amp, and it contains a number of transistors that you can see here. Of course, with integrated circuit technology, it gives us the capability of manufacturing a circuit where all of the active and passive devices, resistors and capacitors, and here's a diode, all integrated together on one small tiny silicon die, which is contained inside this plastic package here. And this particular op amp can be bought for under $1, and it reduces the component price here of the active devices to just pennies a piece. And this is a very, very high gain amplifier that we'll be making use of. However, if you look at the data sheet for this particular op amp, again with under the guidance of Professor Kinaird's tutorial on how to read a data sheet, you can find a line that looks like this that gives the voltage amplification gain factor that you'd expect if you bought one of these and plugged it into your workbench. Here's the line for large signal differential voltage amplification. The units are a little strange, volts per millivolt, but what that basically means is that you multiply the numbers that you see here by 1,000 to get the voltage gain factor. And you can see that for a given part, they'll only guarantee the voltage gain to be somewhere between 50,000 and 200,000 typical, and perhaps even more. There's no maximum specified here. And that's at room temperature. Over the full temperature range, your gain might go down to 25,000 or even 15,000. Well, it turns out that the manufacturing variations in putting integrated circuits together are such that it's very, very difficult and expensive to control exactly the performance, the characteristics of each active device in that amplifier. Plus the basic device physics associated with transistors dictates that the characteristics are going to vary quite a bit over temperature that the circuit is being run at. And so the voltage gain factor, though very, very large here, typically 200,000, is not controlled very well. It can vary over perhaps an order of magnitude. So that's not exactly what we want. What we want is a circuit block to amplify our pH sensor signal with a well-controlled, accurately determined gain factor. So what we're going to do is use this operational amplifier in a feedback amplifier configuration with the use of passive resistors in a feedback loop. Passive resistors are very inexpensive and can be manufactured to have a very well-determined value of resistance coded on the package with these color codes here. And of course we include resistors in a circuit to establish the relationship between the voltage dropped across a resistance and the current flow through it, given by this the nice linear relationship of Ohm's law. The voltage across it is simply the resistance multiplied by the current through it. And the nice characteristic of resistors that we're going to exploit is that their characteristics are fairly stable over temperature, and indeed if you have two resistors in your circuit, the ratio of resistance between the two is quite constant over temperature variations. So we're going to combine a couple of sub-circuits to make our final amplifier. The first is the integrated circuit amplifier, the op-amp itself, and again we use this triangular symbol. There's two input terminals to a differential op-amp and an output terminal. It requires some power being applied. In this case, in this example case, we're running this op-amp off of the 5-volt supply here. And then the other power terminal goes to ground, our reference for 0 volts of potential in the circuit. And the behavior of the circuit for our purposes can be modeled pretty simply by this linear relationship given here, where the output voltage is simply a large gain factor multiplied by the difference of the input voltages applied to what's called the non-inverting input and the inverting input. So that amplifier is going to be combined in our circuit with a simple resistive voltage divider consisting of a series string of two resistors. There's an input voltage here being applied to the top of this voltage divider and an output voltage taken at the center tap here. And from Ohm's law you can derive that the output voltage V2 is equal to the input voltage V1 times a factor here, which is just determined by the ratio of resistances, R2 divided by the sum of R1 and R2. Of course, this fraction is going to have to be less than 1, and so that's why it's called a voltage divider. You get less voltage out at V2 than you put in at V1, but that attenuation factor is very accurately determined and stable over temperature. So we combine these two circuit blocks for our amplifier circuit. We have the op-amp here, and then the output of the op-amp drives the top of the voltage divider, and then the center tap of the divider comes back and feeds the inverting input of the op-amp in a negative feedback configuration. This is going to reduce the gain of the op-amp, and it may seem that we're working against ourselves here by reducing the gain available in the op-amp, but I think I can convince you with a little bit of algebra that this is a very useful configuration. So that the amplifier input voltage is fed to the non-inverting input here, and we can just recall this linear model of the op-amp where the output voltage developed is a linear constant times the differential input voltage across the two input terminals here. Well, the inverting input of the op-amp is just tied to the output of this voltage divider. So I put in the voltage divider formula here using the op-amp output as the input to the voltage divider. And then with a little bit of algebraic manipulation, I encourage you to verify that this is a true relationship here. We can manipulate this expression around so that the output voltage is given by the input voltage times a factor which is a ratio of resistances in the circuit times this other term here. Now this may look like a little bit of a mess, but if you recall that the data sheet of the op-amp guaranteed that the voltage gain factor of the basic op-amp itself was very, very large, at least 25,000, typically 200,000, maybe even more. Well, if we make the assumption that that very large gain is in fact much larger than this ratio of resistors in the voltage divider, which is a very good assumption, then if we look at this term over here, you can see that this term is going to be much, much less than 1, and so that we can make a very good approximation for this whole factor here being basically unity within a fraction of a percent. Very, very good approximation. So basically we can just cross out this whole term in this expression, and we're left with the output voltage of this circuit block being the input voltage times now a new gain factor, which is just determined by the ratio of resistances of the passive resistors in our feedback network. So we've now designed a circuit where the amplifier, the overall amplification factor from the input terminal to the output is very well determined by simply resistor values and very stable over temperature, and something we can design and count on very accurately. So that's basically the design of the amplifier that you'll need in the robots for this design course. I can't resist, however, in this video putting in one more slide just to show you how versatile and powerful these operational amplifiers are. It turns out if you can play around with different sorts of components in the feedback loop and add some capacitors in addition to some resistors, and you can design circuit blocks that realize operators for integral and differential calculus. This is the circuit block for an integrator where the voltage is a function of time, function at the input is integrated at the output, and also a differentiator circuit where the function represented by the voltage waveform at the input is differentiated at the output terminal. So you can actually put together circuits that solve differential equations and do all sorts of useful filtering operations. And you'll get to that if you take courses like EE 2350. But it kind of shows you how versatile these op-amps are, and really that's the origin of the term operational amplifier. You can form circuits that realize mathematical operations. Well, that's it for the tutorial, and I hope that gives you the basics of the amplifier that you'll need for your robot design.